My name is Vlad Khononov. My last name, you can pronounce it however you want. But it's really nice to be first time in a country where you say your first name and everybody is familiar with it. Really love it. So I'm a software architect, I'm a cloud architect. I specialize primarily in distributed systems and domain-driven design. Speaking of which, anybody here already got a copy of my latest book? I see some hands. Keep your hands up if you liked it. I'm watching closely. Okay, rest of you, you know what to do, right? I don't have to say it explicitly, you know, Amazon.com, etc. Just kidding. Anyway, so today I'm not going to be talking about domain-driven design, almost, a bit. But we're going to focus on another subject that I'm really, really passionate about, and that's coupling. And coincidentally, that's the topic of my upcoming book, which is called Balancing Coupling in Software Design. Now, at this point, it was supposed to be published like a year and a half ago. That's what I looked like when I started writing it. That's me right now. So, look, being bad at estimates is a part of our job, so don't blame me for that. Anyway, sometime soon, I will finish it, or it is going to finish me. It will end, one way or another. But today, I want to give you a preview of this book's contents. Now, this is not going to be a sales pitch, like, here's all the great stuff about the book, you will have to buy it in a decade when it's going to be published. No, I want to give you some practical tools that you can apply in an hour in your day-to-day work. And yeah, if it will raise a bit of interest in that book, I'll be happy. So, usually, in my latest presentations, I always have one quote that constantly repeats itself. And in this one, I said, why should we wait for the middle of the talk? Let's put it right there on the first slide. So here it goes. Ruth Malan says, system design is inherently about boundaries. What's in, what's out, what spans, and what moves between. And it's about trade-offs. It reshapes what is outside just as it shapes what is inside. And I wanted right there on the first slide because it outlines the overall topic of this talk, system design, but more specifically, the relationships that span across boundaries involving the thing that we fear the most, that's coupling. And you know, we've always been told that coupling is bad, cohesion is good, and that's it. We also know that coupling slows us down. It cripples our systems, and when working on a system that actively refuses any changes you want to make, we're usually blaming it on coupling. We say that coupling makes things entangled and impossible to change. Not surprisingly, what do we want to do about coupling? Of course, we want to decouple everything. We want to break everything apart into tiny, tiny services or objects or serverless functions or whatever. The motivation is always the same. We want to be able to change every one of those little boxes independently. But what results are we getting by following that somewhat simplistic reasoning? Well, in many cases, we go from coupled piles of code to distributed piles of code. And that's not surprising because, as my friend Matthias says here, going for as small as possible is almost universally a bad advice in software design. Also, Nick Tune puts it, there are many useful and revealing heuristics for defining the boundaries of a service. Size is one of the least useful. And yet, we keep on doing that. Again, microservices, serverless functions, etc. So, I know it may sound a bit controversial, but instead of fighting coupling, in this talk, I want to show you a different way of thinking about it. And I will even try to convince you that we can use coupling as a tool for designing modular software systems. So in the next 40, 50 minutes or so, we are going to explore the nature of the beast that we call coupling. We'll see what coupling is exactly, analyze how coupling manifests itself in different dimensions, and ultimately how we can use that knowledge to design modular systems. Now, this talk was aimed for 40, 50 minutes, but I have 60 minutes. That means I can do all the stuff that people love doing after a good lunch. When that annoying speaker asks them questions and makes this interactive and just doesn't allow people to take a nap. So, sorry. To get the most out of this, let's try to make it interactive. So let's start from the beginning. And you know what? I want to ask you, what is coupling? Somebody. Sorry? Okay, yeah, I like that. I like that. When something calls other something. I like that. So if we go back to the lexical origins of that word, it will take us all the way back to Latin, where it was composed of two words, co and apere. Coapere meaning fastened together. Or, in other words, if two things are coupled, it means they are connected. And that makes coupling a ubiquitous phenomenon. It is everywhere. This clicker is coupled to my computer. Organs in our bodies are coupled to form us, living organisms producing code, or stress hormones in my case right now. One way or another, cars, computers, cities, organisms, companies, for that matter, any kind of system is held together by coupling. You cannot build a system if all of its components are decoupled, if they are disconnected. Simply grouping them together in a boundary, it doesn't provide any value. No, it's just a bunch of fully independent, fully decoupled entities, but that's not a system. For a system, we need these relationships, these connections between the components. So, in a sense, coupling, this is what makes that overarching system greater than the sum of its parts. Therefore, trying to decouple everything makes no sense. Coupling is an inherent part of system design. So again, instead of trying to eliminate it, it's more reasonable to evaluate those inner component relationships and see if they're working for us or against us. Now, for example, let's say that we have two coupled components. The downstream references and thus depends on the upstream component. That arrow between them, that relationship, it defines how these components are integrated. It defines how a change in the upstream is likely to break the integration and require cascading changes in other parts of the system. As Michael Nygaard says, coupling defines the components' degrees of freedom, how freely the components are able to change without affecting the rest of the system. Or, in other words, coupling defines what changes can we make in the upstream here without being afraid to break the integration with downstream components. The interfaces that we are using for integrating components, they have to enable some of the movements, some of the changes, but they also have to prohibit others. Now, it may sound limiting, but actually, we don't want unlimited degrees of freedom. That would render any system overly complex and simply unusable. For example, this clicker, I don't want it to be coupled to my phone, my car, or to that chair for that matter, right? Makes no sense. Unlimited degrees of freedom will lead to chaos. So when designing interactions between components, we want to make sure that we are enabling the movements we need, but we also should prohibit all other possible connections or integrations. We want to align those allowed degrees of freedom with our needs and expectations of future changes in the system that we are building. So that makes coupling a first-class design decision. And going back to Ruth Malan's quote, we want to design what spans and what moves between the boundaries in a way that enables only the changes and movements that we actually need. To do that, we have to understand the dynamics of coupling, how it works and how it manifests itself. And the thing is, coupling is not something unidimensional, like that saying that coupling is bad. It's not that simple. It's a bit more complicated. Coupling affects a system in multiple dimensions: space, time, and the combination of these two, let's call it gravitational force, if you will, the strength of the connection between the two components. Let's go over the 3 dimensions. We're going to start with strength. Now, I have to warn you, this is going to be the most heavy one. That's where we're going to spend most of our time. But again, in order to use it, we will also have to take into account the other 2 dimensions as well. So the effect of strength is probably the most obvious one. It reflects sorts of gravitational force that pulls components together. It defines what is the impact of a change in one place is going to be on the other parts of the system. The higher the strength, the more cascading changes will follow. And as our industry evolved, a number of models were introduced to evaluate that strength, namely coupling in structured design methodology and a model called Khononov. Anybody here familiar with structured design? Khononov? Great. Okay, cool. So we're going to briefly go over these models. Now, I have to warn you. Again, this is going to be heavy, a lot of material. You don't have to memorize this. From now on, you don't have to memorize anything until I say that, okay, now it's the important stuff. Focus on the levels of these models. Focus on the differences between the levels. Focus in terms of the explicitness of the interface. Think about the differences in knowledge that is being communicated across the boundaries. Later on, we're going to use it for formulating a 3rd model, one that we are going to actually use, and then you will have to start memorizing. Okay, so structured design, this methodology, it was introduced back in late 60s. These books, you're not going to find them on Kindle or Amazon, I think, but it's fascinating that today, over 50 years later, we're still struggling with almost the same design issues as it was described in these books. So back then, in the days of Fortran and COBOL, to evaluate coupling, this methodology proposed these 6 levels. 6 levels of interconnectedness: content, common, external, control, stamp, and data coupling. These names make no sense whatsoever for us because they're based on keywords from these languages, COBOL and Fortran. So it's totally unintuitive for us, but anyway, let's see what they mean. And the first one, and the strongest level, is content coupling. And here the idea is simple. One module uses private interfaces, or in other words, implementation details of another module in order to communicate with it, in order to work together with it. Back in those days, for example, go to a specific line would be considered content coupling because you're aware of the implementation details of that second module. Luckily, we don't do such defined stunts anymore, but we have our ways, right? We have reflection, for example. You can use reflection to read the value of a private field, content coupling. You can use reflection to execute a private method, content coupling again. The idea is still the same. Next one is common coupled. And modules are considered common coupled when they communicate through a globally accessible memory space. This shared memory space is an unstructured global byte array. Both modules have to duplicate that knowledge of how that data in that shared memory should be structured. If there is a chance of a change in that structure, both components have to change simultaneously because otherwise the integration is going to be broken. And that makes this level of coupling pretty implicit because that integration mechanism is not properly documented anywhere. And back in those days, this issue was addressed a bit in the next level, external coupling. Here they are still communicating through a globally accessible memory space, but now, instead of just working with a byte array, we have two modules sharing a global variable. It can be a primitive or an array of primitives, but at least the interface is a bit better documented and it is much more explicit than the previous one. By the way, common coupling in our days, for example, if you put a file in S3 and you have two services writing into it and reading from it, that's sort of common coupling that we can introduce today. External coupling when you have, for example, two services working with the same database. Database that enforces a schema. In that case, the interface is documented, but still shared memory space. Control coupling is the most fuzzy one. And the idea here is that the business logic is not properly encapsulated. Instead, it has been spread across multiple modules, and one of the modules have to tell the second one how to do its job. The second one is not autonomous. It doesn't hold all the required business logic. So that's why it's considered a quite high on the coupling scale. Next, we have stamp coupling. And here we have modules that are communicating by exchanging data records. These records are data structures containing way more information than is actually needed for integration. Say I want to call a CRM module and I'm asking for an email for some customer. And instead of an email, I'm getting like dozens or hundreds of other fields. Way more information than I actually need. And sharing that extraneous information, it makes the consumers more sensitive to changes in those data structures, and it overall doesn't really reflect what data is actually needed for integration. It just shares a part of implementation details over the boundary of the component. And finally, we have data coupling. This is the lowest one. And in structured design, it was considered the most desirable one. Here, the modules are communicating by passing arguments with integration-related data only. No extraneous information, the minimum data that is needed for the integration to work. So overall, these levels reflect how much implementation details are shared across boundaries. From content coupling, in which implementation details are used for integration, all the way to data coupling when we are minimizing the data that goes through the wire, and we are ensuring that the integration interface is as explicit as possible. Now, these levels were defined in late 60s, and 30 years later, in the 90s, Miller-Page-Jones proposed a different way of measuring coupling. This one is more adapted towards the object-oriented programming paradigm. He called it connaissance. This word also comes from Latin, and it means having been born together. According to Miller, two components are defined as born together if a change in one of them necessarily requires a change in another component, or if you can postulate a reasonable change that will require both components to change. Now, compared to structured design, here we have a bit more levels. This one is a bit more detailed. And Miller categorized these levels into two types, static connaissance and dynamic connaissance. Let's start with the static one. Static levels, they can be analyzed just by reading the code. They are reflecting compile time dependencies. And the lowest level of static connaissance is the connaissance of name, which means two variables need to have the same name in order to reference the same thing. If you're calling a variable on one line, and you need to specify the correct name of the variable that you are reading. That's connaissance of name. Also, if you are, let's say you are reading a value from a dictionary or a hash map, you need to know the name of the key. That's connaissance of name. Now, another closely related level of connaissance is connaissance of type, and usually these two come together. As the name suggests, here the types of variables they also need to match. So, for example, you need to know whether you should pass an integer or a string. So again, there is no sense in trying to focus only on connaissance of name as the lowest level of coupling. Usually these two, they come together. A slightly higher level is connaissance of meaning. And this one happens when conventions are used to assign meanings to values. A trivial example is right here, status equals 7. What does that 7 mean here? Whoever sets that value and whoever reads that value, they have to agree on the meaning. That's the essence of meaning. We have that knowledge that is being spread across multiple modules that are communicating by exchanging these magic values. Next one is connaissance of algorithm. This one happens when two modules have to agree on use of some algorithm in order to understand each other. A trivial example is, let's say we have two modules that are integrated by exchanging encrypted data. They have to agree on an encryption algorithm they are going to use, because otherwise they're not going to understand each other. So that makes them connaissant by algorithm. Now, unfortunately, there are a lot of misconceptions about connaissance online, and some say that connaissance of algorithm is about duplicating algorithms. No. That would be duplicating business logic, and it would be way higher on that scale. That's something else. Here we're talking about having to agree on a use of a specific algorithm. It doesn't matter if it's duplicated or not. We just need to agree on what algorithm we're going to use. And finally, the highest level of static connaissance is the connaissance of position. This one means that we have modules that are passing values as an array where the meaning of each value depends on its position in that array. Luckily, it's not really common nowadays, but one example would be, let's say you have a send email method that accepts 4 strings, like recipient email address, sender's email address, subject and body, and it makes it really easy to put them in incorrect order, and then you're going to end up with an incorrect behavior. So that makes that method, and whoever uses that, connaissant by position. And the problem here is that such integration interface is implicit. It's hard to track down, and it's easy to make a mistake. So these are the levels of static connaissance. 5 compile time dependencies that reflect how explicit or implicit the integration interface is. Now, again, I remind you, no need to remember this. If you are taking photos, you can, but you don't have to. So that's static connaissance. Now, the dynamic one. These levels, they can be identified by examining the runtime behavior of a system. We can no longer spot them just by reading the code. It's more about the runtime behavior. And the first level here is the connaissance of execution. This one means that we have operations which must be carried out in a specific order, like a recipe, step by step. If you execute them in a different order, you're going to end up with an issue. Can you think of any examples of connaissance of execution? Sorry? Middleware. Middleware. Yeah, that's close. Yeah, yeah. State machines. Yeah, state machine enforces, yeah, the execution, yeah. What happens when we have to work with a database? What do we do first? Yeah, you have to do the migration, but you also have to open connection. Only then you can begin a transaction. Only then you can commit it or roll it back. And only then you have to close it. If you close it before committing, that's not going to work well. The next one is connaissance of timing. And here we have an operation that should be executed in a set period of time after something else happens. So going back to the example of a database, let's say we open connection, nothing happens for, say, 30 seconds. What do? We want to time it out. That makes open connection and timeout connection methods connaissant by timing. We have that set period of time that should pass between the executions. Almost the strongest level of connaissance is value. And here we have values that have to change together. meaning that there is a business rule or invariant or constraint that dictates that these values should change together as an atomic transaction. Or if they don't, the system is going to end up in an incorrect state. A trivial example is, imagine you have a data structure representing 3 edges of a triangle, 3 numbers. If you change the value of one of them, in order for the triangle to remain mathematically valid, you also have to modify the other 2 edges as well. So that makes those 3 values connascent by value. And finally, the highest level of connascence is the connascence of identity. And here we have 2 objects that must reference the same instance of another object in order to function properly. A trivial example here would be, let's say we have 2 modules that operate on the same set of data. So they have to reference the same database, because if they don't, if each has its own set of data and it's not synchronized, the system will end up in an incorrect state again. So that makes them connascent by identity. We have that shared third object that has to be shared between the first 2 modules. So these are the levels of dynamic connascence. The lowest is execution. Again, operations have to be executed in a specific order. And the highest one is identity, where we have that third object that have to be shared between the first 2. Now, it may seem that we can find some parallels between the structure design's coupling on the left and connascence on the right. But these models, they are actually a bit different. And yeah, there is a reason why when I asked if somebody is familiar with structure design or connascence, there were no hands. There is a reason for that. So I want to quickly go over why these models are problematic. So first, it's not really convenient to use terminology from languages such as COBOL and Fortran. If you're discussing microservices and you are saying to someone, hey, that interface, that API is going to introduce temp coupling here. Do it. If you want to sound smart, that works. First-hand experience, do it. But you will have to explain what that means. So it's not really effective. Second, both these models, they have blind spots. So let's think about an example. Say I'm using reflection to read the value of a private field. Where does that put me in the structure design scale? Sorry? Oh, so data coupling, I will start again from the beginning. Content coupling, yes, that's dependency on implementation detail, something that was not supposed to be shared. What about connascence? What do you need to know to use reflection? Name, exactly. So we have one model that says your code sucks. The second one says your code is perfect. Go figure out what to do next. And also there is a blind spot that is shared between these 2, and that's duplicated business logic. Again, duplicated business logic has nothing to do with connascence of algorithm. If we have duplicated business logic, it cannot be spotted by any of these 2 models. So, as I said, structure design, that model was introduced in the late 60s. Connascence is in the 90s. We are in 2020s. And that cadence of 30 years makes now the perfect time to start thinking about a new way of evaluating coupling, right? So let's do it. I called it integration strength. This model, I've been using it for some time now, and I find it way more practical and useful. I want to show it to you. It's basically a remix of the previous 2 models. It's basically the same ideas, but shaped differently. And the focus in the levels of integration strength is on the knowledge that is shared across boundaries of components. And it also has to be practical. It should be easy to use and easy to learn. So for that, we only have 4 levels here: intrusive, functional, model, and contract coupling. Let's quickly go over them. So the first one is intrusive coupling. And as the name suggests, that's a synonym for content coupling from structured design. We are using something that was not intended for integration, but we're using it nevertheless. We're introducing a dependency on implementation details. Needless to say that such integration method is fragile and implicit. The authors of the upstream module, they may not even be aware of that implementation taking place. And second, if something changes in the implementation, we have to assume that it has the potential of breaking our integration. We have to assume that all knowledge about the implementation details of the upstream component is shared across its boundaries. Next is functional coupling. This one means that the connected modules are implementing closely related business functionality. Its practical implication is that the same business requirements, same new business requirements or changes in the existing ones are going to trigger simultaneous changes in both components. The extreme example here would be 2 modules implementing exactly the same business logic. When the requirements are going to change, these 2 modules, they have to change together. Otherwise, the system is going to end up in an inconsistent state. And to make matters a bit more implicit, functionally coupled modules, they don't have to be connected physically. Because if you duplicate the same business rule in 2 objects or modules, they don't have to be connected with each other in order to be affected by those cascading changes. So again, that makes this relationship quite implicit. A lower level of integration strength is model coupling, meaning this one means that components are based on the same underlying model of the business domain. This one is somewhat similar to structured design's stamp coupling. We're sharing a bit of our implementation details over the boundary. If we're going to change that model, the change is going to affect not only our implementation details, but also our consumers, because they are aware of that model. Now, to reiterate the difference between functional and model coupling levels is that functional is more about behavior of the system, algorithms, business rules, etc., while model coupling is more about data structures that we're exposing and can trigger cascading changes. And finally, the lowest level of integration strength is contract coupling. Here, the components are integrated through an explicit integration-specific model that is decoupled from the implementation model, meaning that the implementation can evolve independently without affecting that integration contract. Anybody here into domain-driven design? Cool. So open host service, published language, that's contract coupling. Also, if you're using DTOs for integration, and these DTOs are decoupled from your implementation model, that's also contract coupling. Now, if we compare these 4 levels, we can see that they reflect the amount of knowledge that is shared across the boundaries. And it also reflects how implicit or explicit the integration interfaces are. Intrusive coupling shares the most knowledge about how that upstream is implemented. Functional coupling reduces that knowledge from how to what is being implemented. Model coupling reduces the knowledge to the model of the business domain that is being used by the connected components. And finally, contract coupling minimizes the interface to the bare minimum that is needed for integration to take place. Now, let's say that we have 2 components, and between them we have that beautiful intrusive coupling, meaning that some implementation details are being used for communication. Doesn't mean that the design is necessarily bad. What do you think? No. Wow. Yeah, you're right. Usually I hear it depends. Then I ask, on what? Yeah, you're right. We still don't have enough information to answer that question. To answer it, we need to consider another dimension, distance. Oh, by the way, I forgot to tell you when I need to start memorizing things. So that started with the integration strength section. Anyway, so it turns out the physical location of components in a system, it also affects their level of coupling. And the thing is, the connections between components, they can span different distances. These distances are closely related to what we usually call levels of abstraction. We can have coupling between individual statements or lines of code in a method, between methods in an object, between objects, between namespaces, modules, services, or whole systems. Now, the question is, so here on the horizontal axis, we have different levels of abstractions. We have that red line. What do you think is there on the y-axis? What does it represent? Sorry? Strength? No, but close. What else? Sorry? Bad design. We'll get to it. Sorry? Difficulty of transportation. Yeah, you're really close. Thank you. Yeah, thanks. So, not transportation necessarily, but let's say that we have two components, and they have to change simultaneously for some reason. That line represents the coordination effort that is needed to execute that change. If we're on the left side, that's easy. As we're going to the right side, we need more and more coordination effort. So we can say that the cost of a change is proportional to the distance between the affected components. Now, that's not all. There is another interesting effect of distance on maintaining a system. And that's lifecycle coupling. Or, in other words, how interrelated are their life cycles. As components are located closer to each other, we're getting higher chances that changing one of them will inadvertently affect the other one. For example, if you're changing a line of code in a method, probably it's going to affect other lines of code in the same method. If you're changing, let's say, a signature of a method, probably it's going to change other methods in the same object. And lifecycle coupling actually reduces as the distance increases, hopefully. If you have microservices with high lifecycle coupling, you don't have microservices. Anyway. So, yeah, speaking about microservices, there is another aspect. If you put something in the same physical boundary, it means that whatever changes are being implemented in that boundary, they have to be tested and deployed simultaneously. So that's another aspect of lifecycle coupling. So again, that's something that we have to keep in mind if we want to be able to evolve the components independently. This is just another way of introducing cascading changes. Now, interestingly, distance is affected not only by the physical location of components in a code base, but also by the organizational structure of the company that implements them. Say that we're here on the right side, microservices, and we have two cases. The first one is we have two microservices implemented by the same team. In the second case, we have two microservices implemented by two different teams. In the latter case, we have two teams, and thus we have more coordination overhead, but we have lower lifecycle coupling. So distance is affected by, both by physical location in the code base and by the organizational structure of the organization in some cases. So let's say that we have two components spread apart over huge distance, parts of different systems. Between them, we have that functional coupling, which is pretty high. Is this necessarily good or bad? It depends. Yeah, I shouldn't have said that. Yeah, it depends. We are still not ready to answer that question. And you know what? Let me ask you another question. If a tree falls in the forest and nobody is around to hear it fall, does it make a sound? That brings us to the topic of dimension of time, or volatility. And the main question here is, how often do the coupled components actually change? Now, as the saying goes, predicting is hard, especially the future, but we have some tools we can use to try to predict what parts of the system are going to change the most. And the one I like to use, it comes from domain-driven design, and it's about subdomains. So a subdomain, according to domain-driven design, it's a building block. Say you have a business domain of your system. It's composed of finer-grained business functionalities called subdomains. I was playing with ChatGPT a few days ago. I asked it, please explain me what is a subdomain, but now you're a Jerry Seinfeld. And the answer I got was, well, let's say you're living in Manhattan, that's your business domain. Then paying parking fines, finding parking spots, everything related to parking is a subdomain. So a subdomain is a finer-grained area of business functionality. And the interesting thing about them is we have three types of subdomains: core, supporting, and generic. Core is all about the company's competitive advantage. These involve inventions, optimizations, or intellectual properties that differentiate the company from its competitors. This is how companies make money. On the other hand, a generic subdomain, it's a solved problem. You have a ready available solution that you can use as an off-the-shelf product or an open source solution that you can just buy or adopt, and it's going to be more cost-effective than trying to build it yourself. And finally, supporting subdomains are somewhere in the middle. No ready-made solution exists. You have to write it yourself, but as a generic subdomain, there is no business differentiation there. So that makes supporting subdomain a bit boring. Usually it's something simple. Usually it revolves around a CRUD user interface for data entry or ETL operations, but not intellectual properties, no smart algorithms, etc. And that makes core subdomains the most volatile. Business is interested in changing them frequently to ensure that the solution the business is providing to the customers is optimized. Why are they doing it? Well, because that's going to increase the competitive advantage and ultimately the company's bottom line. So when evaluating coupling between components, we have to also assess the expected rates of change. One way of doing it is domain-driven design subdomains. Another one is Wordly maps. If you're working on a brownfield project, you can analyze the repository to see what parts of the system change the most. That's another heuristic you can use. And that brings us to these three dimensions of coupling that describe the nature of a relationship between connected components from different perspectives. Now let's see what insights can we get by combining them together. First, strength and volatility. The higher the strength, the higher the probability of cascading changes. Again, we're sharing a lot of knowledge. The higher the volatility, the more often we will have to take care of those cascading changes. So when both are high, we'll get high maintenance effort. Strength and distance. Distancing the components physically increases the coordination effort needed to implement a change that affects multiple components. High integration strength over high distance is going to make the system expensive and hard to change and hard to evolve and probably obsolete at some point of time. And finally, distance and volatility. These two reflect the coordination effort that is needed to evolve that system. If both are high, expect communication overload, or in other words, frequent communication between different teams, distant teams in the organization. Now, combining pairs of dimensions, it's still not the whole picture. To get the whole picture, we need to combine three of them. And by doing that, we can evaluate the pain we're going to suffer while maintaining that system. And we can represent that pain by simply multiplying strength times volatility times distance. Now, let's say we have high strength, a lot of knowledge is being shared, volatility, that component changes frequently, high distance, that means that it's going to be expensive to implement those frequent changes. That means that word right there, pain. That's what we are getting. If we want to avoid pain, what should we do? Yes, exactly. Yeah, we have to reduce something, one of them. If all are high, we're getting pain, but following this mathematical reasoning, if we want to avoid the pain, all we have to do is to minimize one of them. So if you can reduce integration strength to the minimum, contract coupling, it's okay to have high volatility over high distance. Cascading changes are going to require lots of collaboration efforts, but minimizing the knowledge that's being shared across components, or in other words, that minimal strength, it will minimize the number of such cascading changes happening. If both integration strength and volatility are high, and there is nothing you can do about it, for example, if the components are naturally functionally coupled, they are implementing closely related functionality, so there's nothing you can do about it. You will have functional coupling, and that's it. You're there. So what you can do to balance it out, reduce the distance between them. Bring them closer to each other. That way, when those cascading changes are going to happen, you're reducing the effort, the coordination effort that is needed to implement them. And finally, if the volatility is zero, well, high strength over high distance won't really affect you. That's why, for example, if you are working with a legacy system, it's okay to communicate with it sometimes through its private interfaces, like going to its database directly or something else, because you know that that legacy system is not supposed to change. So that dimension of volatility, that brings a bit of a pragmatic approach to the design. So the algorithm overall, if you want to minimize the pain, you have to start by eliminating that accidental coupling. Sorry. Reduce it as much as possible. Again, it's not the goal to strive to the contract coupling every time. No, it's not going to happen. Sometimes you need model, sometimes you need functional coupling as well, and yes, sometimes you need intrusive coupling. So if you were unable to minimize the strength, you have to balance it out either by ensuring that volatility is zero or by bringing the components together, or in other words, by reducing the distance between them. Now let's see a few examples of this approach in action. So, sorry. It's a big no-no to share a database between two microservices, right? Now, is this necessarily bad? It depends. Somebody? No. Yeah, it depends on the use case. So let's see 4 examples. So first, it can be intrusive coupling. Let's say we have 2 microservices. That database right here, it was never intended for integration. And the owners of component B, they're not even aware of that integration taking place. That makes this scenario intrusive coupling. we are using implementation details to communicate. Next, let's say that the teams in charge of these two components, they made that conscious decision that they're going to share the database, for example, for performance reasons or any other reason. In that case, that's functional coupling. Now, another common case is for BI systems to go ahead and take all the data from operational databases. In that case, that BI system couples itself to the model being used by the operational system. So that's model coupling. And finally, that database right here, it may be intended for integration purposes. It may hold data for integration. For example, like it happens in the data mesh approach. In that approach, we have a database with integration-specific data. In that case, that's contract coupling. Again, as long as that database, its schema, as long as it's decoupled from the implementation details, as long as we have that protection layer between them. Microservices, why not? So, don't know about you, but I've heard a lot of cases of companies trying to decompose their monoliths, and they start by doing a small POC. So they take a functionality from the monolith, extract it to a microservice, and it works. Then they are doing another POC, and again it works. Then everybody is happy and ecstatic, and they are going full in, and they end up with a distributed big ball of mud. What happens? Well, that POC usually is done on non-critical business functionality, or in the terminology of domain-driven design, on a supporting or a generic subdomain, meaning volatility is zero. But the approach that is being used to decompose that functionality into a microservice may introduce high strength. And having microservices, by definition, maximizes the distance. So during the POC, distance is high, strength is high, low volatility, balance it out, everything is good. Then they proceed to decompose all of it, and suddenly they find themselves with high volatility, with high strength, over high distance, and then they're writing blog posts about microservices being evil. I still have 8 minutes. Well, this is not a domain-driven design conference, so I will give a number of quick examples. So in domain-driven design, we have that aggregate pattern, which minimizes the distance between areas of functionality. And that's because when we are implementing an aggregate, we have to assume very high integration strength, functional. Also, we say that supporting subdomains can be implemented with some rapid application development framework, PHP. That's because volatility is low for supporting subdomains. That's why it's OK. And finally, we have a whole bunch of patterns that help us to minimize the integration strength over high distance. And a corruption layer, open host service, and published language. And with that, let's wrap it up. So coupling. Coupling defines the relationship between components. It's not necessarily good or bad, something that we have to design. It's our design decision. And it happens in 3 dimensions: strength, volatility, and distance. Strength, you can use this model to evaluate the amount of knowledge that is being shared across boundaries of your components. And you can use it at different levels of abstraction. You can apply the same thinking for lines of code in a method and for services in overarching system. We have distance, and this one reflects the coordination effort and a cost of change that the coordination effort and the cost of change that we'll have to take into account when modifying connected components. And it also reflects the component's lifecycle coupling. Volatility reflects how often the components are actually going to change. This allows us to go from idealistic point of view towards more pragmatic point of view on the design. Again, one way of doing it, of evaluating volatility, is domain-driven design subdomains. Also, you have Worley maps, and also you can analyze repositories for brownfield projects. And we have this pain function that shows that you can evaluate the maintenance pain by simply multiplying the values of the 3 dimensions. Now, when and if this book is going to get published, I don't know. But I have to warn you, it's still work in progress. So the terminology I used for integration strength may change eventually. Maybe functional coupling is going to be decomposed into 2 finer-grained levels. That's something that I'm contemplating at the moment. And also the pain function, it's not going to be the culmination of the book. There's going to be another, a more elaborate, more complicated equation that will also take into account the complexity of the system. But anyway, pain function, you can use it right away. And with that, let's see if we have questions. Does it then make sense to couple components based on areas of volatility rather than areas of domain? That depends. If they're changing in terms of volatility for the same reason, I would say that that implies high integration strength. So in that case, the answer is yes. But if they're changing together because of some accidental coupling, for example, you have high life cycle coupling because of low distance, that's a totally different case. I hope that answers your question. If not, I'm here. Next question, isn't the model in model coupling a contract? Why is it undesired? So no, there is a difference. Let's say you have an object model to represent your business domain. You have objects like customers, products, etc., something that you're using to implement your business logic. That's not an integration contract. That's something that you're using for internal implementation details. Integration contract is another set of data structures that are used only for communicating with other components, meaning you can transform the models. You can transform your implementation model into the integration contract. That basically allows you first to have multiple integration contracts when you have multiple versions of APIs that you want to evolve gradually. And it also allows you, to change, to implement, to evolve your model without affecting your consumers. You have that protection layer of the contract. Can having bigger services, modularized monoliths, be considered Goldilocks zone example? Have a reasonably low pain level for most applications? That's a terrific question. Thank you for asking it. But to answer it fully, I need another hour. Unfortunately, on Google, you can look for my keynote from last year's domain-driven design. It's called, what is it called? Fractal geometry of software design. It's closely related to this subject, but from a bit different perspective, and it touches on this question as well. So it's not always the perfect solution. Sometimes you do need to introduce additional distance. What is a good strategy of minimizing pain when migrating to microservices? In my opinion, the best way is to start with logical boundaries. Say you have a monolith. First, you are turning it into a modular monolith with modules representing the services you are aiming for. You are evaluating that decomposition. You are ensuring that all communication across those logical boundaries is enforced, and no one introduces accidental intrusive coupling there. And if that's okay, if you're happy with the integration strength, only then you increase the distance, meaning that you're extracting that logical boundary into a physical one, into a service. I would argue that there should be a fourth dimension, humans. What if one person holding the most knowledge dies, retires, or changes job? That's why we have ChatGPT, we have Dana, who is going to talk about AI. Yeah, sorry, I don't have a serious answer for that. Is the distance the inverse of cohesion? So cohesion basically is low distance with high integration strength. That's cohesion. So in a sense, yeah. And I don't see any other questions, and I have a minute, and that's the perfect time for this slide. Thank you so much.